The force involved in circular motion is always towards the centre of the curve. In other words, in circular motion, the force acting on an object is always perpendicular to the direction of motion of the object. If you are travelling on the object, you are facing in the direction of the object's motion and it is curving to the right, then the force is to the right as well. If the object is curving to the left, then the force is to the left. If there is a weak force, then the radius of curvature will be greater and it will take a longer time to travel around this circle. The same rules about linear motion still apply as before. Speed is distance over time, and acceleration is speed divided by time. The biggest difference here is that it is paramount that you understand the vector nature of motion and define motion in a circle accordingly. Whereas for linear motion, speed and velocity could often appear to be pedantic differences, in circular motion the differences are fundamental. The speed of an object travelling around a circle can be constant, but the velocity of the same object is constantly changing. If you were to plot speed and velocity against time in circular motion, speed would be a fixed positive value and velocity would change following a cosine function as direction changes. The concept of acceleration in circular motion needs some thinking about, but once you understand it properly, you'll understand circular motion much, much better. Although the speed of an object doesn't have to change to undergo circular motion, the direction does. This means that the object is always going forwards and backwards compared to a fixed point in space. If you look at an object from a point outside the circle, where the motion of the object is in line with the centre of curvature in yourself, then the object would appear to move forward for a part of its motion, slowing down all the time. It would then appear to stop moving and then start to move backwards slowly. The object would look like it was speeding up whilst travelling backwards until it reached their maximum speed. This point is halfway from its maximum point forward and its maximum point backwards. It would start to slow down from here until it reached the furthest reach of its orbit. Here it would appear to stop and then return back to its start position, picking up speed until it got there. It would carry on through and repeat the same pattern again and again and again. If you want to see it for yourself, you need to get a bike wheel and attach a stick to it, pointing out perpendicularly to the surface of the wheel spokes. Line up the wheels so that your nose is in line with the tyre. If you spin the wheel, you'll see the stick move down, slow down, stop, and speed up, going up again. This is a perfect description of harmonic motion, covered in another podcast. If you were to look at the wheel from above, you would simply see the stick moving around in circles. If you didn't know that the stick was attached to a wheel going around, you couldn't tell if the stick was simply oscillating or rotating, looking at a side-on view. The object rotating keeps on speeding up and slowing down if you look at it side-on. This shows that there's obviously acceleration at work. From the perspective of a circle, you can see the force acting on the object more obviously. Newton's first law of motion says that an object continues in the same state of motion unless acted on by an external force. The natural state of motion for an object is either moving in straight line at a constant speed or stationary. This object is not travelling in a straight line, so must be undergoing a force. If you were to add up all the vectors of velocity for the full rotation of the object around a central point, you would show mathematically that the force is acting towards the centre of the circle, or you could look at the circle and simply see it for yourself.